I will begin. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Thank you for the students. Just ask you to just bless this class today, Lord. In your name I pray. Amen. All right. So, known Taylor series. So last time I derived sine of x is equal to x minus 1/6 x cubed plus 1 over 120 x to the fifth plus dot 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 dot. This is elegantly summarized as the sum n equals 0 to infinity of minus 1 to the n divided by 2n plus 1 parentheses factorial times x to the power 2n plus 1. This is the so-called Maclaurin expansion, if you like. It's the expansion of sine x about 0. I then pointed out, if we differentiate, we get the power series for cosine, which is 1 minus 1/2 x squared plus 1 over 24 x to the fourth plus dot 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 dot. This is elegantly summarized, the complete power series expansion for cosine, sum n equals 0 to infinity minus 1 to the n over 2n factorial x to the 2n. All right. Both of these expansions are good for all real x. All right. Definition: f, a function from the reals to the reals, is entire if f of x is equal to the Taylor series of f of x for all x in the reals. And to be more specific, I mean, you can pick any point you like, find the Taylor expansion of the function about that point. It will reproduce the function by its Taylor series. So sine and cosine are both like this. If you look at the Taylor series centered around 0, so-called Maclaurin expansion, it reproduces sine and cosine for the whole real line, for all inputs. All right? Not all functions are entire, but sine, cosine, cosh, sinh, and the exponential are all entire. So next up here, let's look at sine, cosine, exponential, cosh, sinh, all are entire functions. Okay, anyway, enough about that. Let me try to redeem yesterday, not by redoing it. No, we're going to leave it there. But let's look at cosh. F of x equal to hyperbolic cosine of x, right? Then what's f prime of x? So what I'm about to do is to derive the Maclaurin expansions for hyperbolic cosine, okay? Let's derive the power series expansion for cosh x centered at x sub 0 equals to 0. So in order to do that directly, I just need to look at the function, right, and its derivatives, and evaluate them at 0, right? Let's see here. So what's f prime of x? Sinh of x. What's f prime prime of x? Cosh x. This is kind of boring. What's f prime 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 of x? Sinh x. I think you see where this is going, right? So dot, 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 dot. you can see that if we have 2k, the 2k derivative of x, we're going to get what? Any even derivative, we get what? Cosh, right? Cosh of x is all even derivatives. The 0th power, the 0th derivative, the 2nd derivative, the however many you like. And on the other hand, any odd derivative is what? Sinh of x, right? That's the pattern that we can see here. Okay, so therefore, what happens when we evaluate at 0? We get 1. For the odds, we get sinh of 0, which is 0. Right? So just let me put it over here just for our reference. Remember, Taylor series generated by smooth f at x naught is the sum, I called it TF of x, right? Sum n equals 0 to infinity. We take the nth derivative, we evaluate it at x naught, we divide by n factorial, and then x minus x naught to the n. I'll reiterate once more the first 3 terms, f of x naught, f prime of x naught times x minus x naught, plus 1/2 f prime prime of x naught times x minus x naught squared. This is the Taylor series generated by f of x. I spent entirely too long yesterday explaining to you that the function is said to be analytic if f of x is equal to tf of x for all x in some neighborhood of x naught, right? So this equality, this means f of, well, it means f is analytic at x naught. If this equality is true for all x in some neighborhood, of x naught. It's always true at the center, right? Because if you just plug x naught into the Taylor series, it reduces to f of x naught, right? So the power series always converges at its center to the value of the function there. So that alone is not enough. But if it converges in some neighborhood, then it's said to be analytic at x naught. All right. So, having that in hand, what is the Taylor series generated by hyperbolic cosine? I say it's the sum k equals 0 to infinity of 1 over 2k factorial x to the 2k power. What am I doing? I'm just using the Taylor series and writing down the terms which are non-trivial, right? So all of the odd terms in the Taylor series for f are 0, right? And all that you're left with is the even terms. What I'm not going to prove to you today is that tf of x is actually equal to f of x. I'm not going to look at the remainder and show you it goes to 0. You can show that, all right? It is true that this is analytic. This being analytic is to say that this is, in fact, yes, equal to hyperbolic cosine of x. That is true. So, we got another one. Woohoo! Cosh of x is 1 plus 1/2 x squared plus 1 over 24 x to the 4th plus ... which is equal to the sum, n equals 0 to infinity, of 1 over 2n parentheses factorial x to the power 2n. So there you go. This is the known Maclaurin series for hyperbolic cosine. Yes, sir.
I don't understand how you derive that, though. Or like, how did you get that from the Taylor series thing from the derivatives?
So I either have if I look at all natural numbers, right? I have 2 times the natural numbers union with 0. Or I have 2n minus 1. I have even, I have odd, right? So if I'm looking at a sum, n equals 0 to infinity of stuff, right? Then I can look at that as the sum, of stuff, even, plus the sum over the odd stuff. This comment is not specific to just this problem. This is a more sort of overreaching general idea that I'm trying to share with you, so I'm being more vague. Saying, generally speaking, if you have a sum over n equals 0 to infinity, right? You can break that into a sum over the even piece plus a sum over the odd piece, right? We have just calculated that for n equals to 2k, if n is equal to 2k, we get cos of x as our derivative, and we evaluate, we get 1. On the other hand, when we have n equals to 2k plus 1, right, k starting at 0, that gives me all odds. Well, those derivatives are all sinh, which evaluating at 0 gives us 0. So as I look at the sum n equals 0 to infinity, which would be the whole genuine Taylor series, half of it is gone because the odd terms just go to 0. And all that I'm left with is the even terms, which all happen to evaluate to 1 here. And so that's what I have. I mean, it's just so hopefully, I think this is less confusing than what I did yesterday. So like yesterday, I broke the sum overall from n equals 0 to infinity into like 4s, right? Like 0, 4, 8. Instead of dividing into even and odd, I divided into multiples of 4 plus 1, multiples of 4 plus 2, multiples of 4 plus 3, right? There's a way I could redo what I did yesterday, just breaking it into even and odd, right? Okay. Okay, great. What's the power series for hyperbolic sine? We can just differentiate the hyperbolic cosine series, right? Because the derivative of cosh is sinh, and we know term-by-term calculus for power series. So differentiating cosh gives me x plus 1 over 6 x cubed plus, well, if you wrote it down, it would be 1 over 120 x to the 5th. And on the other side, we get the sum n equals 0 to infinity of like 1 over 2n plus 1 factorial x to the 2n plus 1. You notice I've taken the liberty of switching k in my example 1, right, to n in the formula up here. Does it matter? Do you see that, like, n and k, they don't have an independent meaning outside of their particular usage, right? It's a dummy variable of summation. Like, this sum k equals 0 to infinity is the same formula as this sum n equals 0 to infinity. The pattern is exactly the same. It's the same terms. Just saying. All right. Now let's finally get to example 2, which should have been my first example last time. This is now our 5th example, which if I was, being a better professor, we would have done to start with. So f of x equals e to the x. Let's find the Maclaurin expansion for f of x equal to e to the x. What's the nth derivative of x equal to? E to the x, right? So what's the nth derivative at 0 equal to? E to 0, which is 1, right? So therefore, e to the x is equal to the sum. I mean, fine. No. So let me just say up here, I'm assuming that the Taylor series generated by the exponential is equal to the exponential, okay? I'm going to assume that exponential is analytic. In fact, it is. All right. Admittedly, there's something to prove there. I should look at the remainder, show it goes to 0, blah, 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 blah. But I really feel like that's more like a 300 or 400 level analysis question than it is a Calc 2 question, so I'm setting it aside. We're saying logically it's there. So what is the formula here? We have the nth derivative at 0 over n factorial times x to the n, and that's exactly just the sum, n equals 0 to infinity of 1 over n factorial x to the power n. There you go. So exponential of x, also known as e to the x, has power series 1 plus x plus 1/2 x squared plus 1/6 x cubed plus ... And that is elegantly rewritten, the entire Maclaurin series here, sum n equals 0 to infinity of, well, 1 over n factorial x to the power n. These are the 5 most important Maclaurin series to have memorized. Now, I say to have memorized, but do you need to memorize them? You could pretty easily derive any of these, right? Because it's not hard to differentiate any of these functions repeatedly and see the pattern. But it's good to have them memorized. All right. Do you see any relation? Yeah. A Maclaurin series just means Taylor series centered at 0. So I say Maclaurin series, it saves me the trouble of seeing Taylor series centered at 0. But it's just that. What's the relation between exponential? What's the relation between exponential and Cauchy sinh? Do you remember what I told you guys at the start of the course? Way back. Remember? I said you can take e to the x and you can rewrite it as 1/2 e to the x plus e to the minus x plus 1/2 e to the x minus e to the minus x, because this is even and this is odd. And I told you we can take any function with a domain which is symmetric about the origin, and we can decompose it into the sum of an even and an odd function. For the exponential function, the even function is what we call hyperbolic cosine. The odd function is what we call hyperbolic sine. Right? I mean, that is by definition sinh, and that is by definition Cauchy. And you see how this story continues at the level of power series, right? If you take the exponential series, right, and you look at the subseries of even terms, what do you get? You get the power series for Cauchy, right? If you look at the subseries of odd power terms, you get the power series for sinh. This makes a lot of sense, right? All right. This is as good a time as any to misbehave. Just a minute. I've behaved so well for the start of class. I will misbehave now momentarily. Fun calculation. What if we looked at e to the I theta? And let's let theta be a real number, but we'll let I be the imaginary number that squares to -1, right? What happens when we look at the exponential series, assuming it still makes sense for complex variables? It does. If you do look at that, then, what happens here? We've got like a 1 plus I theta plus 1/2 I theta squared, 1 over 3 factorial I theta cubed, 1 over 4 factorial I theta to the 4th, 1 over 5 factorial I theta to the 5th, and so forth. let's simplify that. What is that? What are we looking at here? 1 plus I theta. What's I theta squared? That's, so key here, I squared is minus 1, right? What's I cubed equal to? Negative I, yeah. So this is minus 1/2 theta squared. And then we got minus 1 over 3 factorial, minus I over 3 factorial, right? Theta cubed. How about I to the 4th? I heard a 1, yeah. So plus 1 over 4 factorial, theta to the 4th, and then plus I over 5 factorial, theta to the 5th, and then so forth, right? Well, this is a complex series. It's adding both real and imaginary parts. It's interesting, though, to take this complex series and collect all the real part together and collect all the imaginary part together. And so look at that. What do we have? We've got 1 minus 1/2 theta squared plus 1 over 4 factorial theta to the 4th plus dot, 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 dot. All right. Plus I times theta minus 1 over, that's not an I, it's a factorial, oops. 1 over 3 factorial theta cubed plus 1 over 5 factorial theta to the 5th. But what are those? What do we see in parentheses there? What's the first term? Remember what we just derived last class? The power series for cosine. Replace x with theta. What do you got? 1 minus 1/2 theta squared plus 1 over 24 theta to the 4th. Right, that's a 4 factorial. You're looking at the power series for cosine theta. You're looking at the power series for sine theta. And so what we have done is we've just derived Euler's identity, right? Therefore, e to the I theta is cosine theta plus I sine theta. Now, I didn't prove that for you earlier in this course. I just stated it as if it was known by magic. Well, here's the magic which proves it. Yep. What do you mean, which power series off the bat? Oh, that's just the exponential series. So e to the x is 1 plus, it's this thing. This is still true in the complex numbers. Taylor's theorem is still pretty much true. Appropriately, well, anyway. So admittedly, that's the wild jump. To assume that the exponential series still makes sense in the complex number system, it does. But it strikes at the heart of a deeper question, which is how do you define functions? What's the definition of sine or cosine? Have you thought about this? Let me propose to you that a definition for sine and cosine can be given as follows. Sine of x is equal to, by definition, the sum n equals 0 to infinity, minus 1 to the n over 2n plus 1 factorial x to the 2n plus 1. This is a very healthy and good working definition for the sine function. Yep.
Cosine and sine, are they the same as cos and sin?
They are not.
The power series that I see is similar to...
They are similar, but they're not the same. The difference is the plus minus. So the minus 1 to the n is the big difference. But, you can contrast this, right, to e to the x is equal to cos x plus sin x. That's true. Yeah. So you could define sine by that formula. If you define sine by that formula, you can check that it has all the properties that you've come to know and love about sine. It's an odd function. Sine of 0 is 0. right? You also need to define, if we're going to define sine that way, we should define cosine the same way. What would the definition of cosine be? That would be the definition of cosine in this radical new way of thinking. Is the derivative of sine cosine? It is. Is the derivative of cosine minus sine? It is. If you know those two things, you can derive most of the other things you know and love about cosine, like, for example, cosine squared plus sine squared being 1. It's an elementary consequence of the fact that the derivative of cosine is minus sine. You can derive that. So I know, it's kind of fun. And then you could do other things, like you could give a definition for pi. How would you define pi? What is pi as it relates to cosine? That's pi over 2, right? If we're graphing cosine. So you could define pi to be twice the first positive 0 of this cosine function. That would be a working definition for pi, which is completely divorced from geometry. Think about that. This sine and cosine have nothing to do with right triangle trigonometry, right? And if you said pi was twice the first positive 0 of this cosine function, that would give you a definition for pi, which is also divorced of any direct statement about geometry. It's kind of neat. And that's how you can prove things about pi, which you might be surprised you can prove. Anyway, I digress. That's enough. That's all I want to say about that. So, okay, so now we have toys. Let us play with them, all right? Let us play with our toys. What other toys do we also have? Let's talk about tangent, right? Tangent. Let's find the first 3 terms in tangent, the power series, the Maclaurin series for tangent, in 2 different ways. What's the first way we could do? So this is the way you guys gravitate towards. We're going to find first 3 non-trivial terms in power series centered at x equals to 0. We're going to do it in 2 ways. A, by direct calculation of TF, all right? By direct calculation of the Taylor series generated by f of x, all right? And then B, by division of known series. These are 2 quite different calculations. Some of you are stuck. I overheard you talking about the homework. You're stuck on that homework problem because you are too attached to idea A. You haven't embraced the fact that I have given you other ways to find known series than direct application of Taylor's series. All right, so let's do the direct application of Taylor series. A, f of x is tangent. All right. Now, what's f prime of x? Right. I guess I should remind you guys what this means. This is f of 0 plus f prime of 0 times x plus 1/2 f prime prime of 0 times x squared plus 1/6 f prime 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 of 0 times x cubed, and so forth. Tangent is odd. So I know I've not written enough yet. If we want the first three non-trivial terms, we're going to have to go all the way to the fifth derivative. Because I already know that, well, f of 0 is what? Let me clean that up a bit. What's f prime prime of x? 2 secant squared x tangent x, right? F of 0 is 0. What's f prime of 0? What's secant of 0? What's 1 over cosine of 0? It's 1, right? What's f prime prime of 0? It's 0. This is not surprising because tangent is odd. So its even derivatives are 0. F prime 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 of x. Oh man, look at that product rule. This is starting to be unpleasant. For secant of x tangent of x times secant tangent, so that makes it a secant squared tangent squared, plus 2 secant to the fourth of x by the product rule. Yeah? So the third derivative at 0 is equal to what? 2? Yeah. Would you guys forgive me if I took the liberty at this point of crossing out that 3 and writing a 2? Please forgive me if I do that, because I do not feel this morning like differentiating out to the fifth derivative of tangent. Do you? You see why this is a bad approach for this example? I mean, you can do it, right? It may be the only way you have. And you need to be able to do that, and that's fine, but it's going to take you time. And the odds that you make a mistake doing this, they're pretty good, right? 5 derivatives in. What can we see from this already, though? We have that the tangent of x is, so I've got 0 for that. I got f prime of 0 is 1, so I get tangent of x is x. F prime prime was 0. F prime 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 0 was 2. What's 2 over 6? 1/3, right? So x plus 1/3 x cubed plus, well, there you go. I got the first 2 terms in the tangent from what I've already done. So let's try B. Let's try method B. I think that's going to be an easier way to do this. So tangent of x is sine x over cosine x, right? So how did we do long division? Do you guys remember? If I had like 842 divided by 30, I do what? I put 842 here, I put the 30 over there, and I go to town, right? I don't actually need to do this. I'm just force a habit. Remainder is 2, so this is equal to 28 plus 2 over 30, right? All right, so same idea, but with power series. So let's see here. My sine x is like my 842. So what is sine x? Remember? X minus 1/6 x cubed plus 1 over 120 x to the 5th. and then so forth and so on. And what's my power series for cosine? 1 minus 1/2 x squared, 1 over 24 x to the 4th, and so forth and so on. And now we do long division, right? So here goes. What comes up first? To get this, to reproduce the x, I put an x here, right? Multiply by x, I get x minus 1/2 x squared plus 1 over. Now, I should convert the 24th to a 120th. How do I do that? Multiply by 5 over 5, right? 1/24th is 5 120ths. So can you mean adding fractions still matters in calculus? Yes. Never stop mattering. And it's one of the things that continues to hurt you to this day, unfortunately. So many of us were cheated out of the education we should have had as children. Sad. True. X's cancel. A half is how many sixths? 3. So we have to subtract this, right? So we get 3 minus 1, which is 2/6. 2/6 is? Yeah. So 1/3 x squared. And then that is minus 4 over 120 x to the 5th plus ... right? So what's up next? Yeah, it definitely should be. Here I'm lecturing you guys about adding fractions. I can't even add exponents. There we go. I don't say that to be mean. I just say it's the reality which we live in, you know? So that's a cube, right? Yeah. So then to get 1/3 x cubed down there, I do plus 1/3 x cubed up here, right? At this point, we've already recovered the things we got from differentiating 3 times and applying Taylor series, right? So at 1/3 x cubed, that's minus 1/6 x to the 5th plus ... I'm going to stop at x to the 5th, okay? Obviously, if you want higher terms, you need to do more arithmetic and keep more terms, you know? So we take the difference. How many 120ths is 1/6? Yeah, that's 20. That's 20 120ths, isn't it? And so what do I get? I get 16 120ths. And so the next thing up here is plus 16 over 120 x to the 5th, and then so forth and so on, right? But what is 16 over 120? 2/15, right? So we have found that, in fact, tangent of x is x plus 1/3 x cubed plus 2/15 x to the 5th plus ... unless I made an arithmetic mistake, which would be altogether unsurprising. Yeah. I mean, this example, what is worse, doing the long division or calculating the 5 derivatives carefully and applying Taylor series? For some of you, the 5 derivatives and applying the Taylor series carefully is better, right? But this long division is another technique you need to be aware of. It's important for the example in the homework that I'm referencing that you guys were stuck on, because the long division is how you need to find the series for that example, the 1 minus e to the x. You should divide the series to find the first 3 terms in that problem. What problem was that I'm talking about? What number was it? 1 over... For problem 96, I'm recommending you use division of series to find the power series there. let me show you an example like 96, but different. So if I had something like, 1 over, well, let's say x over x squared. No, I'll get it eventually. I have trouble. I'll go with this one. X cubed over, x, sine x minus x. Give me a second, guys. X cubed minus sine of x. There we go. So suppose f of x is equal to this for x not equal to 0, and f of 0 is given to be 0. So find the Maclaurin series. Well, find first I'll say two terms for power series centered at x of 0 equals to 0. My example 4, you're going to have a lot of trouble trying to execute part A because the formula doesn't make sense at 0, so you can't really evaluate at 0. You're going to have a lot of trouble doing the calculation in the style of part A of the last one. You really need to use series calculation here to answer the question. And so the way this works, this brings up another important topic, which is sort of, this is the, oh man. We good. So I think it's okay now. This is always the danger of me making up examples in class, I will try not to modify this example again as we're talking. All right? Forgive me. So what's going on here is this is for x not equal to 0, right? For x not equal to 0. And if x is not equal to 0, that means we can make a simplification, logically speaking. What is this? This is x cubed. So first of all, the x's cancel, right? What can we do at this point? Yeah, we could do long division, but before we even do that, there's something more sort of basic. Yeah, we could factor x cubed out of the denominator, right? We could look at this as, say, x cubed over x cubed times 1/6 minus 1 over 120 x squared and so forth, right? Which is why it's reasonable in the next step here to just leave us with 1 over 1/6 minus 1 over 120 x to the x squared plus dot 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 dot. And then how do you find the first two terms in the power series for that? Here's a thought. this is 6 over 1 minus, what's that? 6 times, multiplying top and bottom by 6, what do I get? I get 1. I get 6 over 120, which was what? 1/20th, yeah? So if I look at this in terms of the geometric series, what do I got? There you go. 6 times 1. Oh, no, there's no minus in the r, right? 1 plus 1 over 120, 1/20th x squared. There you go. Of course, you could do long division and also find the same thing, that the first two terms are 6 plus 6/20th x squared plus dot, 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 dot. If you would do the long division, you should find the same result. You might ask the question, is this application of the geometric series reasonable? It's really only reasonable if what condition is known on R. We need the modulus of R, the absolute value of R is less than 1, right? So as long as we're close enough to 0, this calculation is reasonable. But you got to be careful with this kind of thing. If you get away from 0, it stops being reasonable at some point. Especially if you add higher things in here, which are like fourth powers and so forth. Yeah.
I don't understand how you I don't understand how you went from this step.
I'm identifying it as A over 1 minus R, which we know is A plus AR squared plus dot, 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 dot. So A is 6, and R is 1/20th times x squared plus stuff. And if you think about R squared, it starts at x to the 4th. Think about R cubed, it starts at x to the 8th.
So the first two terms are like what?
Listen, if this doesn't float your boat, we could also do, 1 and then 1/6 minus 1 over 120 x squared. So we're dividing this into 1. So we start with 1/6, right? We start with 6, rather, because 6 times 1/6 gives me 1 minus 1 over 20 x squared. Take the difference, you get 1/20th x squared. So then I say, okay, so plus 1/20th x squared. That gives me, not 1/20th, we do what? To cancel that out, I need I need 6/20ths, right? And then, yeah. So long division will also derive these two first terms by division of series. I was just using geometric series because if I can, I do. Careful to use it correctly, though. We do need that the absolute value of R is less than 1. And in this kind of calculation, you need to make sure that the R squared, the R cubed, and so forth don't meaningfully contribute to the order that you're looking at. See, I know that R squared and R cubed and R to the 4th don't matter here because my R has an x squared. So like R squared starts at x to the power 4. R cubed starts at x to the power 8 and is higher order stuff. Yeah. I will erase while you think of your question.
Why is this a power series and not like a Taylor series?
Power series, a Taylor series is a power series. Taylor's theorem is a specific way of generating a power series to represent a function, but it's not the only way. We can also use the geometric series technique. or division or multiplication of known series. It's okay. Example 5. Think about your question. Ask me again after class. It's here. Example 5. Suppose you have f of x equal to the sine of 3x squared. Find Maclaurin series. This time I didn't say find the first 3 terms. I said find the whole stupid thing. Here's how you do it. Think of this. There's an identity we know. Sine of u is the sum, n equals 0 to infinity, minus 1 to the n, over 2n plus 1 factorial, u to the 2n plus 1. I wrote the formula in x to start with, but guess what? You can make substitutions. Reasonable substitutions. This is a reasonable substitution. And so doing, we find that the sine of 3x squared is equal to the sum, n equals 0 to infinity, of minus 1 to the n over 2n plus 1 factorial, 3x squared to the 2n plus 1. Now, is this the Maclaurin series? Not yet. It's not a power series yet. What was a power series? Remember day 1? It has the form coefficient times x to the power, right? I have 3x squared to a power. That's not a power series yet. I need to simplify this algebraically. Like, is this significant partial credit? Absolutely. But I would take off 10% because it's not yet a power series. You need to clean it up. And so here it is. So that gives me 3 to the 2n plus 1, x to the 4n plus 2. There you go. That's the Maclaurin series for sine of 3x squared. What are the first 3 non-trivial terms? So let me write it down. U minus 1 over 6u cubed plus 1 over 120 u to the 5th. Right? Of course, I could plug it in. I could plug into the formula right above and just look at n equals to 0, 1, and 2. That would also be fine. I'm just saying that if you hadn't already done what's up here, you could start here just the same. Yeah? And if you did that, you should get 3x squared minus 1/6 of 3x squared cubed plus 1 over 120, 3x squared to the 5th power plus dot, 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 dot. And, you know, we should clean this up. So 3x squared minus, I'll be lazy, 27 over 6 x to the 6th plus 80, oh, wait a minute, 243 over 120 x to the power 10. Yep.
Is this another way to find the series, or are we using the information given to us by Postmate there?
We are using the known Maclaurin series to derive the Maclaurin series for this function. We're using the known Maclaurin series for sine. This technique I call substitution. Yeah. So for those of you who love applying Taylor's theorem directly, Take a step back, look at your life. Think about direct application of Taylor's theorem here. Think about generating the Taylor series for this function directly. How many derivatives do you have to calculate in order to get the 3 terms I just wrote down? 10 derivatives. They're not that hard. Oh, wait a minute. Yes, they are that hard. What happens after you differentiate one time? You've got 6x cosine of 3x squared. What happens in the second derivative? It's bad. It's bad, right? It's important to have the substitution technique in your arsenal. You will die without it. You will be overrun by my forces. You will not survive my attack. Prepare yourself. But come on, it's not that bad, right? It's not that bad if you have this idea in mind. Example 6. I'll take a step back here, just do sine centered at x equals to, you pick whatever center you guys want. 2? Okay, so if you do that, I will say you could do direct application of Taylor's theorem. That's fine. It will work out for some of you. It's still a bunch of work. But to my taste, the way to do this kind of problem is to be creative with algebra. So let me show you that. I'll share with you my secret, if you will. And my secret basically is just to use my imagination and to look at this as 2 plus x minus 2. So a gross summary of my techniques. Always use geometric series if you can get away with it. Second, and close behind that, perhaps sometimes in front of it, use the known Maclaurin expansions if you can. They reduce the calculation immeasurably. So, in order to get to the point of using the known results, you have to change what you're given to make it look like one of the known expansions, right? I know how to expand sine, cosine, and these things, right? So I added, this means that I'm looking for an expansion of the form Cn x minus 2 to the n, right? This is my goal. Maybe I should say, goal! Then you'd pay more attention. So there you go. Unfortunately, that comes from a sport I don't care for. So here, so sine of 2. I mean, I don't really care for any sports, so there's that. But as a child, I played soccer for a year, and I don't know, just didn't care for it. I mean, my best friend played soccer at the time, which is why I signed up for it. But then, I don't know, like in the weekend, you're up at like stupid time in the morning, out in wet, rainy fields. You should be home watching cartoons, you know? Anyway. So, oh no, what have I done? I've used trigonometry, right? This is the adding angles formula for sine. Why did I do this? Yeah.
Well, here's that sine, well, sine of 2, because if you're just constants, then you do like substitution thing, the sine of x minus 2, sine of x minus 2.
Right. So this is sine of 2. It's just saying